Hello, welcome everyone. My name is Raka. I'm a doctoral student at ETH Zurich. Together with our partner at the University of Oulu in Finland, we are doing research entitled Life Cycle Assessment of Emerging Processes to Valorize Mine Waste, a case study applied to geopolymer concrete. So let's get going. This is the presentation outline for today. We start by giving introductions why we're doing this, as well as the research questions and the objectives of our research. We describe also our core methodology, which is the life cycle assessment and how we use them. And lastly, we wrap up with the conclusions. So as much as we love renewable energies, EVs, electric vehicles, and also all other technologies for the low carbon transitions, we also need to understand that they have one thing in common, which is material and metal. So when we're doing so, of course, we need to mine more of those materials from the nature. But when we're doing or processing this mining waste, we also produce at the same time waste. So the ratio could be as high as 1 kilogram is equivalent to 160 kilogram of waste being landfilled. And if we are not careful in managing those wastes, we might face environmental issues in the future. Some researchers, such as Raka et al., have suggested some of the ideas to decrease these environmental pollutions, such as desulfurization. So imagine that we are able to decrease the sulfur content, so there might be less acid mine drainage. At the same time, there are also other propositions by Lottermoser et al. So he suggests that basically some of these residues also contain minerals that can be used for the production of construction materials. So we know that these is useful to decrease the mine waste volume as well as the opportunity to increase the economic value. But we also need to realize the challenges. For instance, these mine wastes have different characteristics, so there might be some different recycling options. And most of the time, they are still developed in the lab. So we cannot just say they are viable or feasible. That's how we come up with the research question. So the most important thing would be, how can we determine whether this process is sustainable or not? How do we measure it? So this is just an illustration. We obtained the waste rock sample from our partner from the copper mine sites, basically. And then the question is how we can conduct the environmental assessment. And the main principal method is called life cycle assessment. So we develop models for this life cycle assessment. I'll come back to that quickly later on. And at the same time, since we are dealing with new technologies, so we have to think about how we can scale up these new processes. For those of you who aren't very familiar with the life cycle assessment, or LCA, it's actually a standardized method in order to measure or quantify all the input materials flows, as well as the output flows to the emissions, to the environment. So we characterize them as emissions. So imagine at the beginning, we have the raw material or the mine waste, and then we do some treatments like heating, and then we introduce electricity, and then we also emit some wastewater in the entire value chain. So we need to know what kind of processes being involved and also what kind of inputs and outputs being discharged to the environment. So this is like calling a method that can determine whether a product is sustainable or not. And this will be the main method that we use in our study. Coming back to geopolymer. So geopolymer, according to Davidovits, well, he extensively studied these geopolymer material in about almost 2 or 3 decades. So it's a synthesis of alkaline solution with aluminum silicate powder. So as long as we have these materials, then we are able to produce geopolymer. In our case, we pick sodium hydroxide and sodium silicate as our alkaline solution or alkali activator solutions. We also obtain the mine waste rock, which already contain naturally muscovite and clinocore, which are rich in silicate and also aluminum fractions. And we also need additional water as well as aggregates to strengthen our material to produce geopolymer concrete in the end. This is just an example that our counterpart has produced in their lab. And we eventually want to compare this with the ordinary Portland cement concrete. Here is depicted at the bottom. We define our goal as the production of 1 cubic meter concrete with the specified mechanical strength. This is very important in LT because we want to compare equivalent system. Yeah. And based on our, let's say, investigations, this will be the steps necessary to produce geopolymer concrete. So these are also the foundation of our life cycle inventory data. So we have the grinding in the form of disc milling at lab scale, and later on we add chemicals, and lastly we cure the concrete itself by casting it in this specific equipment, and then later we produce concrete with a specific mechanical strength. We also rely on secondary data to fill the data gaps, for instance, from one of the most extensive review papers about geopolymer concrete recently. However, when we are trying to scale up these processes, of course, they might behave differently. I mean, the equipment would entirely change. And even when we think about like one simple step or process, lab protocol in our lab, basically it involves, of course, some complexity in it. That's why we need to understand how we involve these complexities in our modeling. And one of the suggestions would be to develop life cycle assessment models using process simulator or process modeling tool, such as those suggested by Reuter et al. So the main input data would be the feed characteristics, as well as the unit equipment process parameters that we define for each process or for each block, yellow block here shown on the slide. I'll give you an overview what kind of configurations that are possible in the large scale for our geopolymer making. So in the beginning, we have the waste rock feed here, and then we're trying to separate the inert materials from the non-activated materials. In here, we are trying to activate the materials using high-intensity grinding mill. And lastly, we try to separate the wastewater or tails from the final products. Important to note here is the presence of thickener and mixer, because they are basically separating the products, as I said before. In the second step, we are trying to think about how we can save the water consumption. So instead of using a thickener, we are installing pressure filter plus the equipment to separate water, I mean the wastewater, from the amount of water that we can recycle. By doing so, we are able to reduce the amount of freshwater intake in our process. But also, as a drawback, we need additional equipment or additional pump sum. So that is associated with extra energy involved. We can actually optimize it even further, similar to the second process. Instead of using only one sieve, we can add additional sieve, so that in addition to save water, we can also decrease the, let's say, the effort to pump the entire materials. So we still are able to decrease the water consumption, and we are still able to produce the amount of product similar to the second method or second model. So this will be the summary of changes and also the implications of changing the flow sheets in between processes, in between models. And we do this and we resimulate the LCA for these models, I mean the large scale models, because eventually we will also compare this with a lab scale LCA. So when we compare this with the lab scale LCA, we understand that in all these three large scale configurations, we are able to decrease the energy consumption or energy reduction up to 90% compared to the lab scale. This is thanks to the change of the equipment from small scale pulverizer or milling equipment with 2.4 kilowatt hour per kilogram energy consumption to 0.02 until 0.03 kilowatt hour per kilogram material. So by installing this high intensity grinding mill equipment, which is already mature, which is already reaching its economies of scale, and it also has the process synergies with the other unit processes, we are able to significantly decrease our energy consumption and eventually also make them more competitive. I mean, geopolymer concrete production more competitive. Next, we are now comparing the environmental performance with the incumbents or the cement concrete, the Portland cement concrete. Again, here on the left-hand side, you see that we highlighted the two most relevant impact categories for cement because they are contributing to around 7% of greenhouse gas emissions worldwide. So it's important to know that in terms of climate change, we are able to decrease the emissions level up to 60%. It's the same story, almost the same story for the cumulative energy demand. This is thanks to the prevention of high temperature clinkerization process up to 1400 degrees Celsius in the traditional Portland cement concrete production. So we substitute this by having, let's say, by not even involving high temperature process, but replace them entirely with the addition of alkali activating solutions. However, we also need to understand that by doing LCA, we are not only assessing one or two impact categories, but we also need to understand there are also some, let's say, environmental shifts or burdens to other impact categories. For instance, here, there might be additional increase of 30% of water consumption in our case, despite that we are able to decrease the water consumption based on our different configurations. And some researchers have already suggested that we can even further decrease this even more by replacing the alkali activating solutions entirely or source them from the byproducts or underutilized waste. In summary, this is what we can conclude from our research in terms of competitiveness in the market. We can see that based on our investigations, geopolymer concrete can already compete at large scale thanks to the process simulation plus the expert inputs when we are doing the LCA modeling. So it can already represent the prediction or the large-scale industrial productions in reality. And lastly, about recommendations. First, we have to think about how we can reformulate our alkali activating solutions, which have lower impacts, resource consumption impacts. And we also need to think about how we can extend the boundary. For instance, in our study, we are not involving these leaching tests, but in the future, one can already think about how they should also conduct leaching tests for the finished products to understand the impacts in the downstream when they are using it or disposing the materials ultimately. As an outlook, this is just an example of one LCA for one specific mine waste type. But the idea is also to replicate these types of LCA studies to other mine waste, such as tailings even, since we understand that there are many, many types of valorization options or recycling options for the mining waste. And that is all about our presentation. Thank you for listening. I'm happy to take your questions and suggestions. Goodbye.